Hello everyone, and welcome to the second last topic of this course, digital image processing of remote sensing data. And we have seen various digital image processing techniques, including in the previous one data merging, mosaicing, and image fusion techniques also. And we have also discussed the image interpretations, but now this in this one, not only we will be seeing the examples of image analysis interpretations, but the most important one after interpretation, which comes the inferences. That has to be also incorporated, and this is what the main aim of ultimate aim of remote sensing images is, to exploit to the maximum so that we can get the information about this. This image in the previous lecture, in other lectures I have already shown to you. This is a IRS list 3 image which you are seeing here. This is false color composite, and here you are seeing the 3 reservoirs. One reservoir here, another one is here, and third one is here. Now I am going to use the interpretation keys as well as how inferences can be discussed here or can be made out of this image, and then along with some other data sets how we can exploit and can give insight of this area. But the start point is simple, a false color composite. So 3 reservoirs are located here, and downstream of these reservoirs there is a growth of vegetation. Now this growth may be natural one or a human made. But if you look the area carefully, you would find that the terrain wise the area is same, but in this part where reservoir is there, in the downstream you are having more vegetation, but in other parts you don't see much vegetation because there is no water body. And here also we are having a reservoir, and in downstream you are having growth of vegetation. Even a tiny small reservoir is also having a benefit area in the downstream, whereas these there are no reservoirs here, and therefore the growth of vegetation is very scanty. What is it? And assuming and this area terrain wise geologically is same, then why it is happening? So that means these reservoirs are recharging the groundwater regime, and this is the inference which is coming out of this image interpretations. In image interpretations, we are using keys like color, pattern, associations, everything is being used. And based on that, I have said that there is a reservoir, there is another. And then you don't have the as growth of vegetation as here. So we can assume that probably these reservoirs are charging the groundwater regime. Another important point which also you will notice while doing image interpretation is that if we compare these 2 reservoirs, one is appearing as blue in false color composite and second one is appearing dark. So this blue one probably having the shallow depth or water column thickness is quite less as compared to this one. One can argue that there might be pollutant in it, but from ground information we know that both had the same water quality, except that in this one the thickness of the water column was less, and therefore there is a reflection from the bottom of the reservoir. And in the false color composite it is appearing as blue, whereas here the water column depth is quite thick, and therefore a water body in infrared channel will appear completely dark. Now there is another very important thing which one can, if incorporate some other data sets, can identify about these. So this I will go to this one first, that you are having a digital elevation model, and if you overlay on a GIS platform the positions of reservoir and drainage system, what you would find that reservoir, the smaller one, is located on higher grounds compared to the larger one which is located relatively on lower ground, and therefore it is a recharging. If you see the influence of this small reservoir or the benefit area of this reservoir, which is relatively larger, though size of reservoir is small, But this reservoir relatively is larger, but the benefit area is smaller as compared to against this small reservoir. Now we have to also interpret or investigate why it is so. So if we look again the digital elevation model, locations of these reservoirs and then the drainage system, what we find that since this reservoir is located on higher ground and therefore it is recharging groundwater regime in a much better way as compared to reservoir which is located on the lower ground, though larger in size. Now further inferences we can make out of this comparison between image and digital elevation model, that if we want to make the other areas having also the same kind of vegetation, same kind of agricultural practice, same kind of vegetation growth, then we need to have reservoirs or groundwater recharge structures like this, the blue one, in the different areas here. And if it is done, probably in 1 or 2 years time, the benefits can be seen through growth of vegetation. And I have used this word 1 or 2 years time. I will be showing some examples how quickly in a hard rock terrain the groundwater regime improves once you are having groundwater recharge structures, like in this case. So only in the downstream of reservoir you are having growth of vegetation. Wherever you don't have any reservoir structures, you don't have much growth of vegetation. So these are the inferences which are coming out of image interpretation. One, if you employ or if you use the GIS platform, incorporate some other data sets like a digital elevation model, maybe a geological map, maybe a soil map, and further interpretations on satellite image like lineament, land use, you can create new products which will tell lot many things than a simple image. So image interpretation, and then inferences and integration with other data sets can build up a entire knowledge about that area specific to some problem, in this case the groundwater issue. This is the lithology of that area. This larger area is shown, and there is a relevance but the reservoirs which I was talking are located here. So you are having this unweathered basalt here, it is the unweathered basalt here, in the basement you are having granitic rocks. And now the point which I was saying, that the blue reservoir is on higher grounds, can also be realized in this 3D perspective view. This is on the lower ground and this is on the higher ground. Since it is on higher grounds, it is causing a better hydraulic gradient and therefore better recharge as compared to reservoir here. And this is how the image analysis should proceed. Image interpretation is after enhancement and improvement in the quality of image, the next step comes the image interpretation. And during image interpretations, the inferences should start building up. And if it is possible to integrate with other data sets, then the entire new world can be opened through originally started through with the satellite images. And this flow chart sounds very complicated, but I am not going in detail or each box through this one. But I will show you that when the geological map which I shown of that area, we can integrate in GIS assigning certain weights for these different geology or geomorphological features. So the 4 maps are here. One is the geology map, and only 2 very simple areas have been identified: weathered basalt, unweathered basalt. And from groundwater point of view, different weights have been assigned. So unweathered basalt is more suitable as compared to weathered basalt, and therefore more weight has been assigned. Similarly for geomorphology, similarly for lineament, similarly for slope. And all these 4 maps, and one is coming from digital elevation model, another one is coming from satellite image interpretations. This is also coming from satellite image interpretation. Geology map might be coming from Geological Survey of India or some other sources. And when we integrate along with the groundwater recharge information which is coming from monsoon and post monsoon water level measurements in the observation wells, then we can, this is the linear map, and then we can create a new product through the integration of these maps on a GIS platform. The main input, remember, is the satellite image. Image enhancement, image analysis, image interpretation, inferences, integration with other data sets, and now you are seeing a product which is telling for the same area that this is the, if you are looking for groundwater in this area, then these red areas, just for representation, the red color has been chosen. So these red areas are showing better prospect for groundwater. Whereas if you go for areas which are in this color, this magenta color, then these are the areas where it is highly likelihood of getting water. So you know that why this, because these areas are alluvial fill, there are lineaments, and this is unweathered basalt, lower grounds, and therefore there are very high chances of getting water here, groundwater here. So this is groundwater prospective zone maps can be created for any area, especially this technique can be applied in a hard rock terrain quite easily, employing remote sensing images, their enhancements, analysis, interpretations, inferences, integration with remote GIS data sets or some other data sets on a GIS platform. A new product can be created. And another product can also be created where exactly the recharge structure should come, which are the areas which are suitable for groundwater structure, because we made inferences, we developed a knowledge that if a reservoir on a higher ground, relatively on a higher ground, then it would provide the better groundwater recharge. So therefore, if we apply this criteria over the entire region or our area of interest, what we find, these black areas are the most suitable. They are not at the same level where to the area which we want to provide the benefit. So there are little higher grounds, but not in higher lower order of streams. So they are at not very high grounds, in the middle grounds, but having will influence the hydraulic gradient significantly. So these are the areas most suitable. There are the areas which are moderately suitable, then poorly suitable, the areas where if you go and create a groundwater recharge structure, you don't have any stream, you don't have the slopes available, and therefore the benefits will not come at all. So the white areas are completely unsuitable because they are on the higher ground, they are on the unweathered basaltic rocks, the stream orders are also very low, and their catchment areas is going to be very small. So there is no use of this. So employing all these concept and knowledge, one can develop such products for groundwater recharge purposes. Remaining in the same Bundelkhand region where we are having Bundelkhand Naisik complex, hard rock terrain, and again thinking from groundwater point of view, there is another simple solution which we are seeing here, that if you see this image, now image interpretation is being done here. After enhancement and other things, the image is here, which is a IRS list 3 false color composite image. What we are seeing here, that there are white lines are here, and if one is having little knowledge about the ground conditions, one would know these lines are nothing but the quartz reefs. These are ridges kind of things which are present on the earth. Their genesis, we are not going on their genesis, but these are the raised grounds in a linear form. And the general trend of drainage is from southeast to northwest. So most of these streams either going in this direction or maybe in some other directions. So if the streams are going like this, if there is a quartz reef, in past people have blocked these quartz reefs. That means the drainage which was unchecked going through the quartz reefs, this quartz reef has been used as a dam axis, and that part which was allowing a stream to go through was blocked. And small reservoirs or ponds have been created, which you can see here, 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 here. As in the earlier image interpretation, we have seen that in false color composite, vegetation will appear red. So in the vicinity or in the downstream of these reservoirs, we are seeing growth of vegetation. And wherever the small or large such ponds or reservoirs are there, we are seeing vegetation. And wherever we do not have any reservoir, we don't see any growth of vegetation. So that means that wherever the streams are going unchecked through quartz reefs, those areas can be used to create a dam, a small reservoir, a pond, by checking that stream using that quartz reef as dam access. In past it has been done. There are many streams still are going unchecked, and if it is done, then many areas can also become green. In false color composite, of course, they will appear red in 1 or 2 years time. I will justify this after a few seconds why I am saying in 1 or 2 years time. The effect of groundwater recharge and consequently on growth of vegetation doesn't take much time in these areas, because this is a very hard rock terrain. The aquifers are completely unconfined, and we are having this is as reservoir is full, good rain is there, you are having groundwater for some months of the year. So therefore these groundwater structures plays very important role towards the supply of groundwater. And nature has created these dam axes running for hundreds of kilometers, running between from in northeast to southwest direction. Most of the streams are going from southeast to northwest. They can be checked, and such ponds or reservoirs can be created. Now, what would be the benefit area? What would be the effect? Those things can also be estimated if we do further analysis, further interpretation, and further take out further inferences. Few more examples we will see. There is a reservoir in this, the stream is coming from northwest direction, and it is blocked. In downstream area, you are seeing growth of vegetation as well as in the periphery of these reservoirs. But in remaining areas, you don't see much growth of vegetation. So what we are learning now, this we can call as a submerged area, we can call this as a benefit area. Few more examples. Quartz reef is like this, it is going through and it is creating its own benefit area. Same reservoir downstream is having benefit area. Again, this is the benefit area, this is the perimeter of the reservoir, and this is going roughly from south towards the north. So what we see, wherever we see such reservoirs, we see in downstream the influence, their influence in the groundwater. So we now here in this schematic, we can bring quantities in it by implying a very simple concept of ratio. That this, I consider this is the submerged area, this is the benefit area. So I can create a ratio between benefit area and submerged area just by interpreting a satellite image and measuring these two areas. And it is very easy to measure on satellite images, especially on false color composite. And this is what exactly done in that Bundelkhand region of about 21 reservoirs. What do you see that this benefit versus submerged ratio in some cases is 28, and that what it is indicating that if you invest 1 square kilometer of the land towards the construction of a groundwater recharge structure, a pond or reservoir, in the downstream 28 square kilometer of area will have growth of vegetation or groundwater recharge. So it's a investment in terms of land investment in terms of, and this is 28 times. But there may be some reservoirs like Jamalpur, this example is given, where the benefit is not 1, it is less than 1. It is, the ratio is less than 1. But that means you are investing 1 square kilometer of land, but benefit area is just 0.6 square kilometer. So if I am having more places where this Chanderi and these Jakhora reservoirs are there, or more possibilities in the vicinity or in surrounding of these existing reservoirs, if it is there, then I know that if a reservoir is constructed in this particular area where these reservoirs are located, immediately in 1 or 2 years time, I am going to have benefit of 28%, 28 times, which is a great benefit from groundwater point of view, and that too in an area which is starving for water, at least for 3-4 months of summertime. So this is how we started with simple image interpretation, and this is where we have reached. Still we can employ some more interpretations, inferences and some other data sets, and can do further analysis over this, which I will show you later, this one. I made this statement, in 2-3 years time you can start seeing the benefit. One of the examples, though, is a larger reservoir which was created, which is called Rajghat, in the same terrain conditions. The reservoir started filling in 2001, and this image is MODIS image. It's a true color image, because there are many 36 bands are there, and therefore it is possible to create a near true color image, and this was created. So what you are seeing, the reservoir started filling, and see in just 1 year time, when the reservoir got filling, the growth of vegetation in the downstream area. This is a multi-purpose reservoir, so it has got the irrigation, lift irrigation, hydropower, and of course indirectly it is doing the job of groundwater recharge, which is reflected here, and in 3 years time the whole area is getting green. This is, see how quickly a reservoir is causing groundwater recharge, and that is why I said, if a reservoir is constructed in such areas, today in 2 years time you will start seeing benefits of groundwater recharge, and that can be assessed through remote sensing data in terms of a growth of vegetation, that you can see. Just compare this image with this image, just 2 years time difference. See the downstream area, no vegetation was used to grow there, now you are having, and most of these are agricultural land, agriculture fields are here, crops are growing here. So that's the advantage of doing such a work in a terrain which is having water problem. And it is started, it can be done just first interpreting the satellite images, and can reach to these stages. These are the time sequence. If one see this 4 images, one can argue that one might have been taken a pre-monsoon and then post-monsoon, that is a time difference. No. So what I have tried, I have taken images of the same date of different years. So 1 year after the reservoir was filled, and this one I am talking, and the second year in 2004, 2005 and 2013. This is the situation. So a reservoir, because it's a multi-purpose, it has got irrigation, canal irrigation system, lift irrigation, so water is available on all sides, crossing even watershed limits, and therefore growth of vegetation. So the water was available, only it was flowing as a surface runoff through this Betwa river, and it was not unchecked. Though there in downstream there is a reservoir, but which cannot hold so much of water. So this is holding further large amount of water and creating groundwater recharge structure. Another proof of this one, this was the 1990 image from Landsat MSS, and this is ETM image of 2002, and this is what you see here. See, the reservoir was not there at all, and see the vegetation conditions. This is again true color image. Here what you see, the conditions of vegetation. And there were no new reservoirs have come except this Rajghat one. So we can conclude very easily, attribute to this reservoir, that because of the filling of the water in this Rajghat dam, this is what the growth of vegetation which we are seeing in the surrounding, especially in the downstream of the area. So the benefit area of this reservoir is very huge. Now this interpretation of quartz reefs, inferences, integration with some other data sets, employing some other tools, can build up a further story, and this is what I am going to discuss in this part of this discussion, that this entire Bundelkhand region was taken in this example, and these quartz reefs were also identified using image interpretations. You can use the Google Earth images, or you can use the Landsat images or others. And as you can see that in high resolution satellite images, these quartz reefs can be identified very easily. And this is the ground photograph, field photograph, where you are seeing that quartz reefs are having height of about 30 meter, 25 to 30 meter. And therefore, these quartz reefs can serve as a dam access. These are nothing but the groundwater barriers, doesn't matter. We want to stop the water to flow across these, so that water can be, we can reduce the surface runoff, can hold water for some time, delay the flow, and therefore ultimately it will recharge the groundwater stream. It may recharge in the downstream area, it may recharge in the vicinity or upstream of the area. Some examples are also there, but ultimately availability of groundwater and consequently growth of vegetation, which can be judged, which can be measured through the satellite images of later years. So here what you are seeing, this is again two color images, the quartz reefs are there, but still there are places where these streams are going unchecked. So by employing a digital elevation model or quartz reef map through satellite image, shadow relief model, we can identify those areas where dam can be constructed. Now this is the orientation, general trend of these quartz reefs, which is roughly northeast southwest in direction, and the major flow direction or slopes are towards the northwest, and that's the advantage here. Now there are places which have been identified where quartz reef is there and a stream is going unchecked. As soon as a red part, a burnt part is zoomed here, quartz is running like this. This is the proposed dam, not yet constructed, but on using on images digital elevation model on GIS platform, we can simulate a dam. Not only that one, but what we can do, we can decide the dam, height of the dam, axis of the dam, length of the axis, and then we can calculate what is going to be the submerged area. And this is what it is done here, that quartz reef is taken as a dam axis. The breach part was blocked or assumed that there going to be a reservoir, and once the reservoir of that particular height is decided, this is what we can simulate on a GIS platform, that this is the inundated area is going to be if this reservoir comes. Nothing has happened on the ground, but this is completely modeling, simulation, that this is what is going to be. You can also estimate, if you know the benefit versus submerged ratio, you can also estimate that what would happen in the downstream of this area after 2 or 3 years time. Because we have learned through the successive or time series images that in 2 or 3 years times the benefit starts coming through the growth of vegetation. So this is the profile of that dam which you are seeing here, and the profile of the dam which you are seeing here. This is the field photograph, a river is there, water body, water part can be seen. So if this reservoir used as a dam axis, then such reservoir can be constructed. Since you are having satellite image, so you can also do the create a land use land cover map. So you know exactly that which land part or which land uses will be submerged and so on and so forth. And then exact locations, whose land it belongs to and so on and so forth. Many other things can be done. This is the example here. This is the land use land cover map only for the submerged area was created. So you know that what kind of land will be submerged if at all a reservoir comes at that location. And nothing is happening on the ground. So this is all started with simple image interpretation. So image interpretation, inferences, and now we have reached to the modeling, a prediction part, that this is what is going to happen if a reservoir is constructed here. So this level of image analysis can be achieved in many such cases where different problems are there. I have taken the example of groundwater problems. One can work on maybe some other problems, maybe related with landslides, maybe related with road alignments, route alignments, maybe construction of some other things, and so on and so forth. And this is another example of another reservoir here that you are seeing all this, the quartz reef, submerged area and other things. Now, image analysis for change detection studies. We have seen change detections in different forms while discussing image fusion, image merging. So, remote sensing facilitates, the satellite images facilitates to map where things move, changing condition in space over time. Knowing what has changed can help to understand that how things behave over time, anticipating future condition needs, and evaluate the results of an action or policy. You know, as I have been discussing, that nowadays lot of remote sensing data, and that too time series remote sensing data is available starting from 1972 onward. Though at that time, with reference to today's spatial resolution, we had a coarser resolution from Landsat MSS, 80 meter, roughly 80 meter spatial resolution. But those data sets are also very valuable from change detection point of view. And these data sets are available freely on internet. Just one has to download, register is, organizes on a platform, and then change detection studies related with environment, related with land use, related with any other aspects which links directly with the land can be done. So, change detections, I have given the examples of earthquakes, so I am not going to repeat. Change detections may be flooding, maybe because of forest fire and so on. Results of groundwater recharge, just taken the examples of change detection. Results of landslides or watershed treatments, some treatments are done to maintain the watershed so that deterioration, soil erosion doesn't happen. So those things, if involved, then you can assess unbiasedly what changes the measures have brought in an area. So that also can be employed. And also from long term point of view, change detection can also be done based on the crustal deformation. But these change detections may not be purely based on remote sensing data, but one has to incorporate differential GPS and other things as well. So this example I have already given, so I am not going to repeat, but what I am trying to say that the image, one image in the beginning of this course, it was mentioned that a satellite image tells 10,000 words. So a image or a photograph tells 1,000 words, but a satellite image can tell 10,000 words. I have shown some examples that with a simple satellite image, we started interpreting that image. We have taken out some inferences out of that, then incorporated that knowledge which came through the inferences, incorporated with the other data sets on a GIS platform, created new products, and then reached to the modeling, ultimately at the modeling stage. And we could say that if a reservoir comes here, this is what the effect is going to be in terms of groundwater recharge, in terms of growth of vegetation, or in terms of land use, submergence, or other changes. So similarly, in case of some other large projects, not only the reservoir project, maybe a thermal power plant project, maybe a nuclear plant project, or any such development which takes place, these things can be assessed based on the current remote sensing data, maybe based on the past data, and a futuristic scenarios can also be generated if we develop better understanding interpretations of satellite image. So this brings to the end of this discussion. Thank you very much.